So first, thanks a lot for this nice introduction. It's really a great pleasure for me to speak here today at this Helmholtz Horizon Symposium, so also thanks a lot for the organizers who made this possible. So together with my team, as already said, I'm working on the operando characterization of solar fuel materials, and for this I'm actually specifically working on the development of synchrotron-based soft X-ray spectroscopy techniques that allow us to make operando studies. And in this talk, I would like to give you an idea about how and what kind of insights into water splitting catalysis we can get from this approach. So I will start my talk with a short motivation on hydrogen as a solar fuel, and then I will give you some basic ideas about the synchrotron soft X-ray spectroscopy techniques that we are using. Then I will present to you our most recently developed in situ and operando cell, which is a transmission cell, and I will end with the application, which is in a manganese oxide water oxidation catalyst. As we heard today already in several previous talks, it's one of the great challenges nowadays to replace the fossil fuels by somewhat clean fuels, so basically fuels that not involve carbon dioxide production. And one of the promising candidates in this context is hydrogen gas, simply because it comes also from a very abundant source, basically from water, and also when you use it, basically what you have as an end product is water. And ideally, if you want to produce it in a clean manner, you use for this also a renewable energy source like the sun. And this idea to make water splitting based on sunlight is also nothing new, because basically it can be seen every day in a photosystem too that we have here in every tree around. If we want to mimic this process now artificially, we can do it in such a photoelectric chemical cell, which consists of an anode, a cathode, and in between you have an electrolyte solution. And if you irradiate now the cell with sunlight, you have here in green shown something like a light absorber. Here a charge separation process is taking place, so basically your electrons and your holes are separated. The electrons travel here to the cathode side where they make the proton reduction process, and the hydrogen is produced, whereas the holes travel to the in the anode to the water oxidation catalyst, which allows then to split water up into oxygen and the protons and electrons. If you look at this overall process, the most energy expensive step or the bottleneck reaction is the oxygen revolution reaction taking place here at the anode side. So therefore it is one of the great challenges to develop and to optimize here anode materials which allow to make this overall process also as efficient as possible. If you want to think about large-scale applications, not only the efficiency is one of the big issues, but you also have to think about that you would like to use materials which have a high abundancy, which allow you also to have at some point low costs, and also, of course, they should have a high stability. And in this context, the non-noble metal oxides are quite promising candidates. However, when you compare them, of course, to the noble metal oxides, you will see that there's quite a lot of optimization required, for example, also with respect, besides these parameters, with the surface reactivity. So and whenever you want to optimize such a material on a knowledge-based approach, is what you need to do is to understand this material and these processes down to the electronic structure of your material. And you, of course, if you want to understand the process, you should also study your material while the process is actually ongoing. So you should do it basically with an operando approach. And this is what I'm trying with my young investigator group, with which I start now beginning of this year. And we are doing this by combining it with X-ray spectroscopy here at the BESI2 synchrotron facility. So in this schematic, I would just like to give you a really basic idea about this X-ray spectroscopy, simply what is the principle when we would apply it to a simple atom. What we're doing is that we're irradiating our sample with photons from the synchrotron. The energy of the photons can be then used to transfer an electron from an inner shell to an outer shell. After this, we have here basically a core hole that stays behind, so the system is excited, it will not stay like this. Another electron can fill this place and send out by this again, and another photon. What is the basic principle of this spectroscopy is now what you need to know is that the incoming photon energy as well as the outgoing photon energy are not arbitrary, but they're actually very specific transitions which are only allowed in this system. So this means that with the spectroscopy, on the one hand side, it is element specific. This means I can on the one hand side, learn which element is in there, but this I usually know, but I can also learn, I can specifically excite the element that I'm interested in. And this is, of course, especially important when I go to a complex environment, when I want to study really my materials while they are working, because usually I have a lot of components in there. Furthermore, however, I also get a lot of other information, especially for these transition metal oxides, when I go there to the L edges, about the oxidation states, about spin states, about charge transfer processes, basically also about binding affinities, which are important parameters if I want to make a correlation also to the catalytic activity of this material. So, as I said, if we want to look at these transition metals, we lie basically in the soft X-ray regime to make the spectroscopy there on the transition metal L edges. So soft X-rays go, however, along with a special challenge, and this is that they also nicely interact with oxygen and nitrogen. So this means we can also make nice spectroscopy on oxygen, but the problem is that goes along directly is that they are strongly absorbed by oxygen and nitrogen, thus they cannot penetrate air. So for all our experiments, somehow vacuum is required. I told you at the same time we would like to do in situ and operando measurements. This means we would like to apply potential to our samples, we would like to irradiate it with light, and of course, for this water splitting process, the sample needs to be somewhat in contact to an electrolyte solution that's a liquid. So there we have, accordingly, the big challenge to bring together these vacuum requirements and the requirements you see here on the right-hand side. And for this purpose, we are developing special experimental approaches and tools, and the most recent one, this is the work now of my PhD student Christoph Schwanke, is a very nice soft X-ray absorption cell that works in transmission mode. The heart of the cell is basically here a sandwich consisting of two silicon nitride membranes. One of these membranes has basically two functions. It works on the one hand side as a contact, so we put on top of it a very, very thin gold layer, and on top of this gold layer, this is also the basically the holder for our sample, we put then our catalyst or photoabsorber of interest. The sample is in a direct contact to the electrolyte solution, and this is also valid as well for your reference electrode and the counter electrode. So basically in this unit we have here something like a very small 3-electrode setup. The X-rays for our spectroscopy come here from the left-hand side, so here we are still in vacuum. They go through a first membrane, they enter a helium chamber, then they go through our sample, and they enter here another second helium chamber where we detect them with a gallium arsenide diode. And the reason for this complicated setup to have here two helium chambers is simply that also, of course, the penetration depth for liquids is very low. So basically, if we want to flow in our electrolyte, we need to have here some space. And if we want to start to measure, what we're doing is to increase the pressure into these two helium chambers, and by this the membranes are bending together, that we can really record through a very thin layer of electrolyte and our samples and the gold film and the membranes, then at the end of the day, here our spectra on this diode on the back side. And then we come directly to a recent application that we had. This is a electrodeposited manganese oxide water oxidation catalyst. It's also called manganese pi. As I said, so it can be easily electrodeposited simply from a liquid. It shows a relatively high catalytic activity, and what is especially interesting is actually that it has a high intrinsic and functional kinetic stability in acidic electrolytes. But what you also need to know about this catalyst is basically directly after electrodeposition, it is not yet so highly active, but first it needs to undergo an activation process. So what you're basically doing is that you're applying for a specific time, a specific voltage, and during this time some kind of changes are taking place within the catalyst, and this makes somehow my catalyst more efficient than it is before. And we were interested to know basically what kind of processes are going on within this material during this process, and therefore we basically made a study in which we investigated first the freshly deposited material. We applied voltages and basically saw how does the material respond to this voltage. Then we went through the activation process, so we applied the required voltage for a specific time. We looked there, we monitored there the changes, and then we also wanted to know, is this process actually reversible? So if we apply now a lower voltage, can we basically go back to our original material, or does it change the structure again? And what you see here on the right-hand side are our manganese LH spectra of a freshly deposited sample. You see here when we vary the apply voltage, we also have here spectral changes in our spectra. So we basically, just to give you a short idea, we analyze them by making a linear linear combination fitting with several reference samples of manganese oxides, where we could think about these could be likely species that could appear in this material. And to give you a general idea, when we look here at lower oxidation state materials, they usually have your features in lower regions, whereas more intensities appear in higher regions when we go to higher oxidation states. So to give you a first idea, this means when we have this freshly deposited film, we can see here in the different spectra, when we go from low voltage to high voltage, we have simply a systematic change from low oxidation states to higher oxidation states in the material. So then we have here the activation process and the reduction process. And again, in the activation process, we have the parameter is now here the time, so we recorded spectra after 1.5 minutes up to 51 minutes. Here we applied 1.2 volt, and in the reduction process, we applied 0.3 volt, and monitored also the changes again, kind of if we can make this process reversible. And to give you an idea about the results that we got from this, basically, I made it just as a schematic. When we start with a freshly prepared film and we apply the high voltage at which actually water oxidation is running, we see first that we have a contribution of around 75% manganese O2. This is basically a material with an oxidation state of 4+, whereas we have something like 25% of a material that is rather bernesite-like. So bernesite is a material that has an oxidation state between 3 and 4. Basically, what is the difference to the MnO2 is also that we have here now a two-dimensional layered structure where we have an intercalation of ions and water within the structure. When we increase now, when we apply enough potential for longer time, so basically run here through the activation process, what we see in our data is that the contribution of MnO2 is actually systematically decreasing, whereas the contribution from bernesite is significantly increasing up to 75%. So basically what we see here is that somehow our material is changing, that we get here an intercalation of ions into our structure, which we would then correlate somehow to the, to the catalytic activity of this material and the efficiency of this material. Furthermore, we can see when we apply now lower voltage that this is also somewhat reversible, this process, so that we can back to a higher percentage, this is now 59% of manganese O2, but also we can go to structures that are rather have an oxidation state like manganese Mn2O3 with the oxidation state of 3+ when we kind of disactivate this sample again. So this is basically the first step also to go towards these operandum measurements. What we're currently doing now is that we are combining now the catalyst, which is now just basically on the gold substrate on a photoabsorber. We use the bismuth vanadate. And what we are then monitoring is not just what happens when we apply voltage, but also what we shine light. And then we can basically directly see how the charges or the holes are then transferred to our catalyst and see then how this affects the oxidation states in the material. So I hope I gave you a short idea about what kind of information we can obtain with these techniques. This has, of course, also wider application than just the material I showed to you. Basically, all kind of materials, whenever we are interested, oxidation state changes or charge transfer changes can be monitored with such approach. At the end, I would like to thank the Helmholtz Society for the funding of the Young Investigator Group, and I would like to thank my colleagues from the Solar Fuels Department here at HZB, and I would like to thank my current team members. And of course, I would like to thank you for your attention.